Welcome to the session on simple cases in fluid flow as part of the NPTEL MOOC on transport phenomena and materials. In this session we will be looking at applications of the pipe flow equation that we derived earlier to porous bodies. So, here we have the solution that is written already. We have derived this in the previous session, where due to the pressure drop per unit length that is shown here, the pressure at left hand side of the domain is shown as pH, right side is PL. So, the pressure drop is given as minus of delta P by L. So, therefore, that is the driving force for the fluid flow in the axial direction, and the average velocity, that is which is half of the maximum velocity, is given as r square by 8 mu into delta P by L. So, this is also referred to as Poiseuille flow, and when we look at the mass flow rate by the same problem, then that would be called as the Hagen-Poiseuille equation. So, this equation should not be applied for any range of pressure drops that we like, but when the Reynolds number that comes out is less than 2100. So, after we solve a problem to determine the average velocity through a pipe due to pressure drop or body force rho g, for example, we need to multiply the velocity with the diameter and the density, divide with mu, and check the Reynolds number that comes out is small. So, that is when the laminar flow assumption is valid, and therefore, the results will be correct. So, beyond this number then we cannot use this expression. So, here we want to just look at this equation in a slightly different manner. The same equation which is written earlier, you can then compare that it looks somewhat like the Ohm's law. So, the velocity, the average velocity of the fluid through the pipe is like current, and the delta P by L is the reason why the flow of the fluid is actually happening. So, it is like the voltage or the driving force for flow, and what goes as the denominator, that is 8 mu by r square, that is proportional to 1 by r square, that is like the resistance to flow. So, it means that pipes which would have narrow diameter would be requiring more pressure drop to have the flow take place at the same magnitude, etc. So, once you compare, you could already see that we have a analog, electrical analog. So, the current is like the flow, the pressure drop per unit length is like the voltage, and we do have a quantity that comes like a resistance. So, just like one would solve the circuits problems in electrical engineering problems, then you could also do the same thing with the pipe flows. So, whenever you have a network of pipes, for example, in situations like this, for example, so in situations like this, what happens to the flow and what would be the pressures at different junctions, etc. These can be solved using the same analogy. You could also solve them piece by piece, but that would be a little more tedious. So, when we have the pipe not exactly a circular cross section, then what do we do? So, here is a concept that could come of use for us. The concept is basically hydraulic radius. So, when we look at the volume through which the liquid is flowing, which would be given by the cross sectional area, which is pi r square into the h. So, that is the volume through which the liquid is flowing through, and the wettable surface area, that is the area which is actually in contact with the fluid, that is the surface area which is impeding the motion of the fluid. So, that would be basically perimeter times the h, and if you take the ratio of these two, you would see that the radius will be arriving at from the volume divided by the surface area. So, volume is actually also the void volume. So, you could actually qualify this as void volume, because it is through this void or cavity that the liquid is going through. And once you have this, you could actually imagine that you can always call the ratio of volume to wettable area as a relevant quantity for the radius, and which you would actually now define now. So, we would like to define what is called the hydraulic radius. So, we are actually creating a new variable called hydraulic radius, and we want to define it as a ratio of the void volume over the wettable surface area. So, once you have this, then non-circular cross sections of the tubes can also be handled, and you could also then try and see whether the expression that we derived earlier could be applicable when the deviation from the circular cross section is not very much. So, at this juncture we actually are going to apply the pipe flow equation to a very different set of problems and see how interestingly the relationships are coming out to be similar. So, here is where we are introducing the new concept called the porous media or porous bodies. In daily life these are very familiar to us. We know from bread, for example, these regions you can see that there is a lot of porosity, and these actually are seen in engineering also and very common. So, you could actually see that you have a porous body, an aluminum foam which is used to absorb shock, and it would collapse. The porosity would help the material collapse and thereby absorb the energy before the impact is passed on to the contact body which is behind. So, you also have situations where extended surfaces, porous surfaces are available like here, which can be used to remove the heat. So, the air that is in between these solid surfaces would take the heat and go away, and thereby lead to heat transfer taking place very efficiently. So, a lot of heat exchangers would have their appearance looking like a porous body. And you also have seen porous bodies in granular materials, as you would see in bubbles or grains or sand particles or pulses when they flow. So, during all these phenomena you would see that the domain basically is a porous body and a porous medium. And in metallurgical scenario this is very much important, because apart from heat exchangers, filters for example are very much porous bodies. Basically if you have a bed of alumina spheres, then you could use it to filter the dross from the liquid aluminum melt, and therefore you could actually use porous bodies for filtering liquid metals. Liquid metals are very corrosive, so you could not use a metallic sieve to do that particular kind of a thing. And as you can also see from the appearance that porous bodies have a lot of surface area that is available. So, which also means that reactions that take place on surfaces can also be enhanced. So, catalytic converters are also generally porous bodies, and you also have multiphase reactors that would have porous bodies. One of the reactants will be made as these porous medium, the other ones will be like fluid going through, and then because of the extended surface area that is available, reactions can take place at more area, and that can be useful in enhancing the productivity. And the pressure reducers, when you want to reduce pressure across a length, then introducing a porous body in between generally helps. So, like this there are a number of applications in metallurgical industry where the porous bodies are coming across. And when we have a situation where a fluid is going through a porous body, what kind of an expression can we use? So, this is where, for example, we can see whether what we have learned till now can be applied. So, a very generic way of representing porous body would be like this, where you have got the white regions would be like, for example, the solid, and the black regions would be like the void. Okay. So, what this implies is that when you have a fluid that is entering from one end of the body, so it would actually go through the void which is interconnected and eventually come out. So, you could see that the path is actually tortuous, nevertheless it is available, so that the fluid can go through the porous body. Now, it also means that you could also have a bed of spheres, each sphere made of the diameter dp, and the black here is the void, and this is a solid sphere. Then you could also have the situation where fluid can go through the void that is available to go across the porous body. Okay. So, in both these situations, for example, you could treat that there is a certain amount of void volume that is available for the fluid to go through. And one situation that we want to now use is the path that is taken, can we then imagine that to be like a tube. So, we want to actually check can this path be imagined as a tube through which the liquid is going through. Okay. So, our idea of modeling the phenomenon is basically assuming that the void, interconnected void, is similar to a tube, and then see if what we have derived till now can be applied for this kind of a problem. Okay, so let us try if this works. So here we now introduce some terminology to characterize a porous medium or a porous body, so that this will be useful for our derivation. So one characteristic of any porous body is to tell how much of porosity is there. So you should tell the porosity as the first characteristic. If you take for example a powder bed and then you are using powder metallurgy principles to sinter it to a solid block, then depending upon the extent to which sintering is happening, you would have porosity changing. So as the density approaches the theoretical density, the porosity is approaching 0. So intermediate, if you stop, then you can achieve the porosity to be something between 0 and 100. So like 50% porosity, 70% porosity, etc. These are all possible. And so you would like to define the porosity as the volume of the void to the volume of the porous body itself. Okay. So by porous body, what we mean is the entire body externally measured. So if you use a calipers and measure the dimensions, then that would be the volume of the porous body. And if you were to remove all the void, then that would be the volume of the solid, and together is basically what is coming as V. Okay, here what we refer to as V. Okay. So V epsilon then becomes the volume of the void, because from the definition V is this, and therefore V epsilon would then be the void. Okay, so that the ratio becomes V epsilon by V, that is epsilon, which is basically the porosity. Okay, so the porosity is one characteristic. Now it is possible to have porous bodies which have the same porosity, but they may be made of particles of different diameter. Okay, it is possible to achieve that, and in such situations what happens is that a body which is made of particles of a smaller diameter would have a more tortuous path for the fluid to go through, and which also means that the surface area that is exposed will be more. So it is possible to have the same porosity but different particle diameter internally, that would actually give you more surface area. So you need one more characteristic feature, so that is basically the surface area per unit volume of the solid. So surface area per unit volume of solid is one another characteristic of the porous body that you can define, and this can be actually measured experimentally, and so we define one more quantity here. Okay. So from whatever we have seen till now, you could actually then use these two quantities to arrive at what would be the hydraulic radius of the pipe, which we are imagining as basically equivalent to the interconnected void. So hydraulic radius, we have already seen, it is the ratio of the void volume to the wettable surface area. So the void volume is coming from the first definition, and the wettable surface area is coming from the second definition. So that RH is coming out to be an expression that involves two characteristic features of a porous medium, namely epsilon and S naught. So once we have the RH, then this is what we do. So we then look at how the flow is taking place. So here we have drawn on the top surface the pressure is high pressure, and at the bottom surface you have got the low pressure. So you could see that then it should lead to the fluid flow to happen in this direction. Okay. Now if the pressure difference from the top and bottom surfaces is given as delta P, and the height of the porous body is L, then delta P by L becomes the driving force which is causing the fluid flow or the fluid to go through this porous body. Okay. Now the porous body would have a volume V, and the ratio of V and L would basically give you the surface area or cross sectional area of the body. So we call that as A. Okay. Now this A is the area of the body, which means that it can be measured by using calipers looking at the width and depth of the body. And this cross section, when you look at the cross section, you could then see that it is also made of voids and solids. So you could also see a fraction, you could also look at the fraction of void in the surface there, and if that is assumed to be same as the fraction of void in the entire body, then we are actually calling this particular porosity as isotropic porosity. So, what we mean by isotropic porosity is that area fraction of void is same as the volume fraction of void. It is also the same as length fraction of void. If you draw a line in random direction and then count how many segments of the line are falling in the solid and how many are falling in the void. Okay. So, isotropic would mean that in any direction the way of counting actually will give you the same void fraction. So, if that was true, then A epsilon would then be the area of the void through which the flow can take place. So, A into 1 minus epsilon would then be the area of the solid through which the flow cannot take place. So, we now look at the entire volume of the fluid that can go through this body and see how it can be represented. It can be represented in two different ways. On the left hand side, we have one way of representing, and here we write an expression in this form. So, there are two terms. Okay, the first term is basically the void area, and which means that whatever is going through the void is actually going at the actual velocity. So, this basically is the actual flow. Okay, so U is actual flow. So, flow into the area of cross section will give you the volume flow rate. So, that is quite acceptable as we have seen till now. However, this is not useful in the sense it is very difficult to measure the actual flow rate through the voids, because the voids are very small and they are of different sizes in different locations in the body. Okay. So, what actually is useful is to check what would be the superficial velocity. So, superficial velocity is defined in this manner, that is, it is a velocity as if the fluid is going through the entire cross section of the porous body. So, A into US should give us the volumetric rate. The reason why we call this as a useful quantity is because this actually implies I could actually calculate it as V dot by A. Now, V dot can be actually measured because you could actually collect fluid that is coming through this porous body for a duration of time and then divide the volume with the time, and you get the volumetric flow rate. And you can actually measure the area of the porous body by using a calipers, and therefore, this can be measured. So, which means that the superficial velocity of the fluid as if it is going through the entire cross section of the porous body can be experimentally determined, and so that is actually also determining the volumetric flow rate. Now, the way you determine volumetric flow rate in both ways is the same. So, it is the same fluid that is going through. So, if you want to then draw an equivalence between these two, then that is possible when, for example, the actual velocity is equal to superficial velocity divided by epsilon. Okay. So, this is how we are able to now relate the superficial velocity and the actual velocity. Now, for the actual velocity, we do have a relationship available because it is going through the void, and for flow through the void, which is roughly in the shape of a pipe, then we do have an expression that is giving us a relationship between the velocity and the these two, the delta P by L, through the pipe flow equation. So, now we want to relate these two and see how it comes about. So, we are basically now making an assumption, that is, if the porous body is treated as a bundle of tubes. Okay, so, each connected void is like a tube, then the actual velocity, if it is related to the driving force for the flow through the hydraulic radius, then maybe we can use the pipe flow expression or Poiseuille flow expression for connecting these quantities. So, we are just blindly going to apply that equation, which we have already seen earlier. Only difference is that this is related to the superficial velocity, and this is related to the porosity and the wetted area for unit unit volume of the solid. So, we substitute those expressions, and you see on the left hand side it is US by epsilon, and on the right hand side RH is equal to epsilon by S naught into 1 minus epsilon, which we have already seen just a while back. Okay. So, we basically use this expression here, and then we basically are able to see how pipe flow is applied to flow through voids of a porous body. Okay. So, we are basically modeling the porous body as a bundle of tubes, and for each tube we are basically able to write this expression. Okay. So, which actually means that we can then take the quantities back and forth and see that we are able to relate the superficial velocity with the driving force, and it is going through a bunch of quantities that are actually as a coefficient. Okay. Now, this coefficient you can inspect the trends when epsilon is going towards 1 or towards 0. So, when epsilon goes towards 0 means that there is no void, which actually also should mean that it is a fully solid, and it would require infinite pressure drop to lead to any velocity, and that would actually be also evident because they are coming as multiplication. Okay. So, for a given velocity us, if epsilon is going towards 0, then delta p by L will blow up. Okay. That is what we also expect. Okay. So, what we are now doing is to just see if we can make a generalization of this particular model to arrive at an equation that has a name. So, the equation that is available in extractive metallurgy literature is the Blake-Kozeny equation, and we will see whether we can arrive at that. So, what we actually want to do is these entire coefficients that are there in front of the delta p by L, we want to just simply call that as k. Now, what happens is that what does k do? So, k basically tells you that it is the ability of the porous body to let the fluid go through it. Okay. So, it is basically telling you how efficient will the pressure drop convert into the velocity. Okay. So, if it converts to give you high velocity, which means that it allows the fluid to go through very easily, and if it does not do that, it means that it causes a lot of obstruction to the flow going through it. So, which means that it is nothing but permeability. So, permeability coefficient is what we want to call k as. So, which means that we are now relating velocity to pressure drop per unit length through permeability, and the permeability coefficient which is written with empirically verified functional form is here. So, this is a expression that has been derived separately. So, you could see that the only place where we actually got it a little off is here. So, we see that this is the only thing we did not get right. Other than that, the functional form is exactly how we have come about, and this expression is empirically obtained and verified. So, which actually means that this quantity is a correction factor to take into account the fact that the void interconnected voids are actually not bundles of tubes, but they do have other effects. For example, whenever you have got bundles of tubes which are actually also interconnected, then there must be some effect because of that. So, some pressure drop will be modified because of that, and therefore, it must lead to some correction factor. So, let us see that basically this is a correction factor, otherwise our model seems to work quite well. Okay. So, Blake-Kozeny equation is basically, except for this correction factor, a model to treat the interconnected void as a bundle of tubes and then applying the analytically derived pipe flow equation to it. So, here this goes a little further. So, independently there is another equation that came about a little earlier, which goes by the name Darcy's law, and here basically the same equation we are writing, and because we are now noticing that the superficial velocity is a velocity. So, it is basically a vector. So, you have got a vector, okay, and this entire thing is nothing but the coefficient, and this is pressure drop per unit length. So, delta p by L is basically, in our case, it is dou p by dou x if the velocity happens to be in the x direction, and so therefore, it is like gradient p. So, this is also a vector. Okay. So, from what we have studied earlier about the constitutive relationships relating cause and effect. So, if you want to call this guy as cause and this is effect, that is due to pressure drop an effect, namely the fluid flow is taking place. So, if you want to think of these as cause and effect, then this must be a property. Okay. And as per the tensorial relationships that we have seen, that if cause and effect are vectors, that is tensors of order 1, then the property can be in most general case a tensor of order 1 plus 1, that is 2. So, we then basically go ahead and write that expression. So, this is a tensor of order 1 and this is a tensor of order 1. So, therefore, this must be a tensor of order 2. So, that is why we basically refer to the permeability as a permeability tensor. Okay. So, permeability tensor is a very generalized concept. So, which means that the equation that we came about by starting from the pipe flow equation and then modeling the porosity and then introducing the concept of hydraulic radius, then once we got that equation, if we want, we can elevate it to the level of a constitutive relationship between cause and effect, then we do arrive at what is called the Darcy's law. So, Darcy's law is this equation, and in which the permeability is coming as an anisotropic tensor of order 2, and you could actually call it as isotropic in situations where the medium is isotropic. So, if the porous body happens to be isotropic, then you can go ahead and write k I j as k into delta I j, and in which case then you could actually see that US is then given by k into delta I j p, that is basically k into p. So, you could see that you actually see a vectorial relationship giving only a constant here for the case of isotropic medium. So, by Neumann principle, the property should have the same symmetry as that of the material. So, if the material happens to be isotropic porous medium, then the property also should be isotropic, and in which case you get the relationship that we have already seen. So, in that way we can actually see that starting from one equation, we are lining up another equation which actually all came very early, almost independently, and the relationship is coming out quite beautifully thanks to the tensorial concepts that we have seen till now and the models that are interconnecting these. Okay. So, now we see that we can actually check for the validity of these relationships. So, the way to validate is the same as for the pipe flow. So, to look at the Reynolds number and checking whether the Reynolds number is within some range or not. So, the porous medium has been modeled with these quantities being a bit different. The u is basically the superficial velocity, and here the Reynolds number should have actual velocity. So, we must then substitute properly. The diameter is basically twice the hydraulic radius. So, we must also bring the hydraulic radius expression. So, we bring that in and we see that the Reynolds number will come out to be an expression like this. So, normally when we have non-dimensional quantities, then we do not want numerical things in there, because there is no point in that. So, we can actually look at the introduction of non-dimensional numbers as only a way to remove the dimensions. So, numerical values need not come. So, we redefine. So, we redefine the Reynolds number in this manner by knocking off the 2, and to remind us about the redefinition, we actually also pay attention to the subscript which actually tells us that there has been some redefinition that has happened. So, the Reynolds number for a porous body is given by this expression, and the results that we have seen till now, that is the Blake-Kozeny equation, is valid when the Reynolds number with the new definition is less than 2, which you can see that it is 1000 times lower than the Reynolds number for a pipe flow. So, definitely our model that we have applied is applicable only when the flow is very slow. So, the moment it increases, then our model does not seem to work. Okay. Now, we can then go ahead and apply the same concept to a bed of spheres that would act as a porous body. The only reason why we want to take it up is because we do have a simpler expression that can come out. So, the bed of spheres is depicted here. So, the pressure is high at the top surface, it is low at the bottom surface, and therefore, the fluid flow will take place in this direction, and that is happening in the voids spaces that is interconnected and coming out. Okay. And we want to model that particular path as a tube, and we are just basically going to use the same expression. So, the diameter of each solid sphere is dp, which actually makes us assume that the bed is made of unidisperse solids basically. So, if you have a distribution of sizes, then we are not yet able to handle that. And it is then also clear that the epsilon can still be varying because once you have got the particles, you can arrange them differently to get different void volume. Okay, so you can make them close packed, we get less volume, we get loosely packed, then we get more volume. So it's showing that epsilon can be independently controlled, though the particle diameter is already fixed. Okay, but once the particle diameter is fixed, then the wettable area is also getting fixed, and that is basically here. You can see that the wettable area is given by ratio of is a product of S naught and volume of solid, and we can see that if there are n spheres, then n into the surface area of the sphere, that is the numerator, and n into the volume of the solid, that is the denominator. The ratio would give you the S naught, and that comes out as a 6 by dP. So, which means that this entire quantity is dependent only on dP. So, powder diameter is directly controlling how much of wettable surface area is available per unit volume of the solid. So, here we are actually making a very important assumption that there is only a point contact. Okay, so there is no loss of surface area because so many powder particles are coming together. So, we assume that the area of these two is exactly is equal to twice into this. Okay, so there is no loss of surface area, we are assuming. So, subject to that, then we go ahead and substitute wherever S naught is available, we are actually putting 6 by dP, and then we will see that the K expression would have 4.2 into S naught square, and that is approximately 150. So, which means that we now have an expression also where the porous body is made up of uniform spheres of same diameter dP. Okay, so the K, that is permeability coefficient, is now available for us as an analytical expression with epsilon and dP that are there. Now, epsilon, if we already know that it is close packed with, let us say about 68% packing, then you already see that 32%, that is 0.32 will be the value of epsilon, and then the diameter is available. So, dP can be substituted, and with the viscosity of the fluid available, immediately we can get what would be the permeability coefficient. Now, once that is there, then we can substitute in the Blake-Kozeny equation and see how that would look like for the bed of spheres. So, for the bed of spheres, I have just flipped the quantities around to show them in the way that most textbooks show. So, delta P by L is equal to 150 mu into 1 minus epsilon square by epsilon cube dP square into US. So, this expression actually is there in many of the extractive metallurgy textbooks, and we know from where this has come. So, this has come from our model and the fact that S naught happens to be 6 by dP for a bed of spheres. Now, this is valid when the Reynolds number defined appropriately for this problem happens to be small. So, very low Reynolds numbers, and that actually is now modeled here. We already see that this can be modified to 6 by dP, so which we have done, and we do not want in a Reynolds number definition. So, such things are actually not required. So, we go ahead and redefine the Reynolds number, and we pay attention to the subscript, and we see that it has been defined in a different manner. So, with this definition of Reynolds number, then if it is less than 1 or very small Reynolds numbers, then we can go ahead and use the Blake-Kozeny equation for a bed of spheres here, and this would actually relate how the pressure drop per unit length is changed because of the velocity that is going through, which we desire. So, which also means that if you want a particular amount of pressure drop to happen, then you can actually see that knowing what is be the velocity of the fluid going through, then you can actually ask yourself what is epsilon that you would need to achieve that kind of a pressure drop. So, that way we can actually put these things to great use. So, at this moment we will close. The numerical problems using these expressions will be made available as practice assignments in the course website. You could punch the numbers and see how you are getting through.